Hello and welcome back. The last part of this packet of notes talks about some common polar equations and their graphs. R equals a sine theta and r equals a cosine theta, the graphs of those are both circles. So the sine thetas are going to be along the y direction, so kind of along the y axis, and the cosine theta version is going to be along the x-axis. That kind of makes sense because we said that sine theta has this symmetry about the y-axis. That's why the circle is kind of along the y-axis. And then cosine theta has a symmetry about the x-axis. So that's why the circle is along the x-axis. So I'll just note a couple of things here. One is that you go around the whole circle when theta goes from 0 to pi. So if you allow theta to run from 0 to 2 pi, it turns out you go around the circle twice. Once for positive r values, and then once for negative r values. And then one more thing I'll mention is that the circle goes through the origin at some point. So the center of the circle is not going to be the origin, it's actually going to be just a point on the graph of the circle. The center will be more like whatever the coefficient is of either sine or cosine divided by 2. That's where the center will be. So if you look at the coefficient, halfway will get you to the center, halfway from the origin will get you to the center, and then the full way across will get you to the other side of the circle. So the coefficient in front of sine or cosine is really going to be talking about the diameter of the circle, either in the y direction or the x direction. For roses, like are in figures 15, 16, 17, and 18, for roses, those are of the form a sine n theta and a cosine n theta, where n is some kind of, typically it's like an integer, but it doesn't have to be an integer necessarily. It'll just look like a funny looking rose if it's not an integer. So here, like, we could have maybe 4 sine 2 theta. Now what that's going to do is it's going to create these petals, and for even coefficients in front of theta, you're going to have twice as many petals as that number in front of theta. So since there's a 2 in front of theta, you're going to have 4 of these petals. Now the way that you travel along these petals is something like this. If you draw this in the r theta plane first, and then you map those over into the xy plane, you're going to travel along the first petal going counterclockwise, and then you're going to jump into the 4th quadrant to continue drawing because you're going to have some negative r values coming out there. And then you'll go into the 3rd quadrant where you'll have some positive r values. And then the 2nd quadrant where you're going to have some negative r values. And then back to the origin where you're going to start over again. Back into the 1st quadrant, then the 4th quadrant, then the 3rd quadrant, then the 2nd quadrant. So that's the path that a rose takes. For sine theta, you're going to have the first petal inside of the 1st quadrant. For cosine theta, because of that symmetry about the x-axis, the first petal will be kind of straddling the x-axis like that, so it'll be along the x-axis. And in fact, the coefficient in front of the cosine is going to be how far out your petal is. Actually, that's true for all of these. 4 is going to be the distance from the origin out to the tip of each petal. So 4 will be the distance from here to here and out to each petal. But you can see it more clearly when it's along the x-axis because you're going to have a scale of 4 in the x direction to help you there. Again, if there's a coefficient of 2 in front of the theta, you're going to have 2 times 2, which is 4 petals. Now, if you have an odd coefficient then in front of theta, then you're only going to have that many petals. Because when theta goes from 0 to pi, you're going to go through the petals once, and then from pi to 2 pi, you're going to go through exactly the same petals over again. So they'll draw on themselves over again. All right, so the path that it will take is going counterclockwise around the first petal. It'll jump into the 3rd quadrant momentarily, and then into the 4th quadrant, and then jump over to the 2nd quadrant and back to the origin where you're going to start all over again. So that's just the journey from 0 to pi. Then from pi to 2 pi, you go through the whole rows again. Now it's jumping back and forth between these quadrants because like from the first to the third, because the r value flips from being positive to negative as it crosses through the origin. Another type of common polar equation is called a limacon. These are ones of the form r equals a plus or minus b sine theta and r equals a plus or minus b cosine theta. And the shape of the limacon depends on the a and the b values. So the summary is that if a is greater than b, then there's no inner loop. We're going to see an inner loop in just a moment. So the limacon looks something like this. It's kind of like a circle, but it's a little bit dented on one side. If a is less than b, then there's going to be an inner loop. So here we have r equals, in figure 21, we have r equals 2 plus 3 sine theta. There the a value is 2, the b value is 3. So we end up getting this inner loop that's created by the fact that sine theta will eventually become -1, and then you'll have a negative r value overall. So that's going to make that little inner loop. We actually found that inner loop in one of our examples. I believe it was example 6. If a is equal to b, then it's a cardioid. That was I think example 5. That's where as you're going around, you jump into the origin just for a moment and then you bounce back out of the origin. Example 5 was aligned along the x direction. It was a cosine curve, but for the sine curves, they're going to be along the y direction, right? The sine, if you have a sine theta, it's going to be symmetric about the y-axis. If you have a cosine theta, it's going to be symmetric about the x-axis. Whoops. Oh, so that was the last kind of curve. Thought there was one more. Oh well. Thanks for watching, and see you next time.